shall we start?
Okay, sir.
Okay, sir.
Yeah. Can you see the screen? Right.
Yes.
Yeah.
So we'll look at the other types of footings like inverted T. But before we look at inverted T, we'll have a quick look at strip footing just to see why inverted T's work better. So basically, when you have number of columns at regular intervals, then you might consider having one footing rather than isolated footings. So if you're having isolated footing, there's an advantage that you need the main reinforcement only at the bottom. Whereas when you have combined footings or strip footings, you'll need both top reinforcement and bottom reinforcement. And if you are having columns that are loaded not equally, you might get non-uniform pressure distribution as well. So basically, if you are having fairly stiff footing on good soil conditions, then it's possible to get a reasonably uniform pressure distribution. On the other hand, if you either have a weak footing or weak soils, there is a possibility for some non-uniform stress distribution due to the ground. So we look at both options, both possibilities, and see what are the important things we have to consider. So if you have columns carrying approximately equal loads, the design method is fairly straightforward, and that is, we can select a suitable width for the foundation. If you know the load acting through the column and the bearing pressure, if you know those parameters, then you will be able to select a suitable width for the foundation when the columns are located equally spaced. So if they are equally spaced, then we consider midpoint to midpoint. The load here will be effective midpoint to midpoint, and that way you can work out something reasonable for the bearing pressure. So first we have to look at the size of the footing, that is the width of the footing. And then we have to check for punching shear at the face of the column, just to make sure that concrete will not fail in crushing. After that, we can check it for flexure and direct shear, and also punching shear if applicable. So we look at an example and see how we can design this. We'll not spend a lot of time on this, but just to get some idea. But if you are having a set of columns like this, then and if you assume a uniform distribution corresponding to these values, then if you do not want to do a computer analysis, then it's possible to get the bending moments that you need for design by using this particular manual for design of concrete buildings, building structures to Euro Code 2 by Institution of Structural Engineers. By using this manual, you will be able to select the bending moments, provided the spans are more or less equal, and we can assume a reasonably uniform pressure distribution under the base. Then The bending moments at the support can be considered as 0.1 FL. The bending moments in the midspan can be considered as 0.08 times FL. And shear forces can be considered as 0.65 times F. So we can make use of these values and do the design. On the other hand, if you want more accurate results, you can use a computer program and find the bending moments and shear forces as well. So for this example, we'll make use of these values. So design a strip footing to support square columns 400 by 400 located spaced equally at 3.5 meter centers. On each column, the characteristic load is 1000 kilonewtons permanent and 350 kilonewtons variable. And it's a fairly good soil, having a safe bearing pressure of 200 kilonewtons per meter squared. And the characteristic material strengths are, we'll use 30 megapascal concrete and 500 megapascal reinforcement. So here we are talking about a column every 3.5 meters. So we also need to have a reasonable stiffness, because if the footing is too thin, then we cannot get a situation of uniform stress distribution. So let's assume that we are going to use a thickness of around 800 millimeters, and you can even try 600. So here I have decided to go for 800 millimeter thickness. So it's a fairly thick base, 800 millimeter thick base, continuous, and we have to see what is the width of the base, and also we have to do the routine checks that we need after determining the reinforcement required. So when you look at the base, it will carry a permanent load of 1000, variable load of 350, 1350, and also we'll see what is the net bearing pressure we can allow on this, because due to the self weight, we don't get bending moments. So, but still we have to allow for self weight. So the allowable bearing pressure is 200, and that should include the loads transferred to the columns plus self weight of the base. So on the other hand, we can make use of the net bearing pressure. That means from this 200, we can deduct the allowance for the self weight of the base. Self weight of the base is 0.8 multiplied by 25 kilonewtons per meter squared, or 20. So self weight of the base is 20 kilonewtons per meter squared. So from the allowable bearing pressure of 200, we can deduct 20. Then we'll end up with a net bearing capacity of 180. And we can make use of this particular net bearing capacity of 180 for our calculations. And because the columns are located at 3.5 meter spacing with a net bearing pressure of 180, we can select a suitable width for the base. And we select a width of 2.2 meters. And so once you select the width of the base, we have to do this reinforced concrete design for ultimate limit state. So to do the design for ultimate limit state, we have to find the maximum pressure that can be exerted by the soil. So to find the maximum pressure that can be exerted by the soil, we find the ultimate load 1.35 GK plus 1.5 QK divided by the area represented by each column, 2.2 meter wide and 3.5 meter spacing, will give us a pressure, maximum pressure of 244 kilonewtons per meter squared. So with this pressure, we can check for punchy shear, and we can also check for the reinforcement requirement and so on. So first thing we do is, now we have selected a thickness of 0.8 meters. Let's check the punchy shear carrying capacity. And that is at the face of the column. That is at the face of the column. So at the face of the column, we have a perimeter of 400 plus 400 plus 400 plus 400. That is 400 into 4 is the perimeter. And we can select the maximum shear that can be carried. And the maximum shear that can be carried is given by 0.5 times nu times FCD. And FCD is equal to FCK divided by 1.5. The value of nu is given as 0.6 times this expression, 0.6 times this expression. And then we have 0.5. And if you want the shear force, you have to multiply the shear stress by the punchy shear perimeter. Punchy shear perimeter is 400 into 4, that is the length. The thickness is the effective depth. And the effective depth for 800 millimeters, we consider an effective depth of 740 millimeters, allowing for cover of about 40 to 50 millimeters. So, which means we can substitute in this equation and find the maximum shear that can be carried through a column. And you can see we will end up with a fairly high value, 6,251 kilonewtons. Whereas the maximum that you can get through the column is 1,875 kilonewtons. So through the column we can get 1,875 kilonewtons, whereas the base of 0.8 meter thickness can easily carry 6,251 kilonewtons without any compression failure induced by shear. Which means, the selected thickness is more than enough. It's not a problem at all. Then we can decide on the reinforcement. And so to determine the reinforcement, I said that we'll use this simplified method. The bending moment at the support is 0.1 FL. And F is the total load in each span, and L is the span. Total load on each span is equal to the pressure that is acting from below multiplied by the width of the footing, 2.2 meters. That will give the line load, equivalent line load. And then when you multiply that by 3.5 meters, you get the value of F. So F is equal to 244 multiplied by the width of the base. So 244 multiplied by width of the base will convert it to a line load. And the span is 3.5 meters. So which means the value of F is 1,879 kilonewtons. And then multiply that by the length multiplied by 0.1, you can see the bending moment is 657 kilonewton meters. And once you know the bending moment, you can find the K value. And then if it is less than 0.167, you can simply reinforce it. And you can see the effective depth is D. And the Z value is 0.95 D, which is 703 millimeters. Which means, using this equation, the area of reinforcement multiplied by strength of reinforcement multiplied by lever arm is the bending moment, or area of steel is equal to bending moment divided by 0.87 FIZ. You can see 2,148 millimeters squared. Reinforcement is needed in the longitudinal direction. And then you can also check the minimum reinforcement requirement. And the problem with all this type of very thick bases is the minimum reinforcement requirement also can become significant. And the minimum reinforcement requirement for 30 megapascal concrete is 0.15. 25 megapascal concrete is 0.13. So we have discussed those things last time. So you can see the minimum reinforcement governs, and we are deployed about 8 numbers of H20 bars as the bottom reinforcement because we considered the moment at the column. And at the column, it is bending in such a way that tension occurs at the bottom. So this is the bottom reinforcement. And you can see the bottom reinforcement. What we need is 8 numbers of H20, and that is represented by the minimum requirement of reinforcement. So, and if you look at the span, the bending moment is lesser. The mid-span, the bending moment is lesser. But here, even for this case, it's governed by the minimum reinforcement. So, which means here also the minimum reinforcement will govern. So, we can provide the same reinforcement at the top as well. So, at the bottom and top both, you will provide 8 numbers of H20 bars over a width of 2.2 meters. Over a width of 2.2 meters. So this, just by considering that it will bend upwards and downwards depending on the location, and the reinforcement requirement for flexure is governed by the minimum reinforcement even for the higher bending moment. So we can provide the minimum reinforcement everywhere as top reinforcement and bottom reinforcement. Then in addition to that, this particular base cantilevers from the column line, and the width of the base is 2.2 meters. So that means in the transverse direction, it has we can say it cantilevers a certain distance. Because these columns are located far apart, like 3.5 meters, if you want, you can assume that, it cantilevers from the center line. If you want, you can assume that it cantilevers from the center line rather than on the face of the column. So here in this particular example, I have considered to calculate the transverse reinforcement that the base is cantilevering 1.1 meters from the center line of the columns. If I want, I can even consider the face of the columns as well. And the pressure from below is 244. Cantilevers 1.1 meters means 244 into 1.1 into 1.1 divided by 2. So you get a moment of 148 kilonewton meters. And kilonewton meters per meter, and considering that Z is equal to 0.95 D, we can select the reinforcement because these thicknesses are so high, so the 0.95 D generally governs the Z value. So straight away I have used 0.95 D, and I got the reinforcement as 490 millimeters squared per meter width. And if you look at the earlier example also, 0.95 D governs. So here also I have considered 0.95 D governs. And then when I look at the minimum reinforcement, again you can see the minimum reinforcement is governing. And when you look at this minimum reinforcement, you can provide something like H20 bars at 250 centimeters. So in this particular example, you can see, because this minimum reinforcement governs, we need a lot of reinforcement here because the flexural requirement is only this, but the minimum requirement is higher. So we are needing a lot of reinforcement in the transverse direction, and that is one of the disadvantages of this type of strip footings. That is one of the disadvantages of this type of strip footings, because the cross-sectional area is large. The minimum reinforcement tends to govern, and the minimum reinforcement minimum reinforcement requirement can be much higher than the requirement for flexion. So that is one of the main disadvantages of this system. Then we can also check the same footing for punching shear and direct shear. And if you look at the size of the footing, 2.2 meters of width, 3.5 meters of length, and then what matters is the punch and shear perimeter around it, around the column. And because we are having a depth of 0.8 meters, then which gives an effective depth of 740 millimeters. You see 2D is outside the base. 2D is outside the base. So basically punch and shear may not be a major problem, but we can also check for direct shear. And when you are checking for direct shear, we have to see what is the direct shear, and direct shear is given by 0.65 times. You can see the direct shear is given by 0.65 times F at the face of the support, So which means we can find the direct shear force a distance d away from the face of the support. So the shear at the center of the column center is 0.65 times F. That is 0.65 times 1879, 1278 here. And at a distance 0.74 away, we can find the shear force, and that is this shear force 1278 minus whatever shear in 0.2 meters and whatever shear in 0.74 meters due to the force that is acting from below. And the force that is acting from below is 244 into 2.2, and then you will end up with 773 kilonewtons of direct shear force. And if this shear force can be carried only with the carrying capacity of concrete, then this footing may be okay. But on the other hand, you can even consider providing the minimum links. So let's look at the design value of shear resistance, which is given by this equation of 6.2a of the code, which also has a minimum value given by this expression. And CRDC is 0.12, and K is a parameter that depends on the depth. And the reinforcement is, we are providing 8 numbers of H20 bars over a width of 2200 with the effective depth of 740, 0.0154, and that is the row value. And FCK is 25 or 30. We are using 30. Yes, we are using 30 here. FCK is 30, and you can see the shear carrying capacity of concrete alone is 0.303, and that will give a shear resistance of this shear stress multiplied by the area in 10 to the power minus 3. And we also have to check the V minimum value, and V minimum value is given by this expression. V minimum value is given by this expression, and last time also we used this V minimum. So you can see V minimum is 0.36. So the minimum force that can be carried by the section is not 493, it is 586 kilonewtons. But so basically without any reinforcement, the section can carry 586 kilonewtons, but it has to carry 773 kilonewtons, which means this section has failed. So we have to provide the links. We have to provide the links. So we can also check shear carrying capacity if minimum links requirement is fulfilled. And the minimum link requirement will be given by this expression. Last time also we used it, so I will not spend much time working out the minimum stress, the minimum requirement for shear. And it is 1.97, and which means X16 bars are selected. The spacing is going to be around 200 millimeters. The spacing is going to be around 200 millimeters. And if you calculate the corresponding shear capacity, which is given by this expression, then you will find the minimum V value that this section can actually carry is 1450. So basically, you can see concrete alone can't carry shear. But if you are providing reinforcement, then you have to provide fairly high quantity of reinforcement. That is, T16, H16 bars at 200 as shear links. So 16 millimeter bars as shear links. And if you provide that kind of shear links, you can see the shear carrying capacity is 1450. But what we need is only 773. But we can't provide only 773 because the minimum is governing. Here ask the question why it's all happening. It's all happening because we have selected a beam which is having a massive cross section. It is having a width of 2.2 meters, a thickness of 0.8 meters. So we are having a beam having a massive section, and because of that reason, these minimum parameters are governing. And you can clearly see the use of a rectangular section as a strip foundation is actually cannot be justified. And because of that reason, we prefer the use of inverted T-type foundations. So basically this example is included to show you that the strip type foundations having large cross section is not very economical. Flexurally, it's not having a major problem, but when it comes to shear, if the section can't carry the shear, you have to provide the minimum links. And if you are providing the minimum links, it will need a lot of links, a lot of reinforcement just to fulfill the minimum requirements. So strip footings may not be that economical unless the loads are small. But if the loads are reasonably large, this type of foundations will not be economical. And the economical foundation type will be this one, and what we call inverted T-type foundation. Inverted T-type foundation. So we spent little time working out the details for these inverted T-type foundations because some of the things that we learn here can be used for various other types of foundations as well. So basically what I want you to appreciate is this type of, strip type foundations having a width of 2.2 meters, a thickness of 0.8 meters. They are not very efficient. They need a lot of concrete and a lot of steel. And worst is, it needs a lot of links. So it's not a very economical type of foundation. So now we'll go into the more economical type of foundation, and that is inverted T-type foundation. So if you are going with inverted T-type foundation, then we are actually relying on the stiffness of this beam, which can be fairly deep, which can be made fairly deep to provide adequate stiffness without consuming too much concrete. And then to spread the load onto the soil, we are relying on this flange. And when it comes to the flange also, it is reasonably efficient because if you consider the bending moment on this flange, it will be caused only by this projection. It will be caused only due to this projection subjected to the pressure from underneath. So generally the bending moment at this particular section will not be very high, which means, by providing some reasonable quantity of reinforcement in the transverse direction, we'll be able to resist the loads acting on this particular part of the flange. Same on this side. But when it comes to the providing the shear links, and one of the things you can observe in the early example is when it comes to the minimum links actually depend on the width of the base. Minimum links actually depend on the width of the base. So this is the equation for minimum links, and the equation for minimum links actually depend on the width of the base. So if you can actually have a width which is small, like this one, then the penalty for the providing shear links also will not be high, because the minimum requirement for links will not be a very high value. But if you have a complete full width, then because the minimum requirement depends on the width, you might end up with a fairly high answer. So when it comes to this type of foundations, inverted T-type, we can actually design it as a flexible foundation or a rigid foundation. First, we will look at it as a rigid foundation. We'll look at it as a rigid foundation. So this type of foundation can be designed as rigid. Design will be very similar to the example presented with the stiff foundation. So I'm again looking at the same example now with an inverted T-type footing. Now I'm looking at the same foundation with an inverted T-type footing. And the strength of concrete also 30 megapascal, 500 megapascal reinforcement. Safe bearing pressure of 200 kilonewtons per meter square. So any questions on this? Now we are going to look at this inverted T-type foundation. So the first question is, what is the depth of the foundation? What is the depth? Now, you can select a depth like 600 millimeters, whereas I have selected a depth of 900 millimeters. That is the first thing. So you can select any thickness, but because we like it to be fairly rigid, we can be little generous with the depth of the foundation. And you can also see the depth of the foundation will not have a major penalty because we are having extra concrete only over this particular width. Then the next question is, what is the width of the foundation? What is the width of the web? What is the width of the web? Now, when it comes to the width of the web, you have to consider the fact that the column reinforcement also goes through this. So there are two options. The column is wide, column is large, you might be able to select thickness less than the column, say 50 millimeters less than the column, so that the beam reinforcement can go inside the column reinforcement. On the other hand, the column is small, like 400 by 400, then you can select thickness bigger than the column size, so that the reinforcement of the beam can go through the column without any cranking. So you don't have to bend the reinforcement to accommodate the column reinforcement. The beam reinforcement can go outside the column reinforcement. So there are two options available. One is, sending it within the column, and if the column is small, you can send it outside the column. So either way, you can provide it. But if the column is long, like elongated column, then you might consider providing some links for the beam within the column size. Otherwise, over a longer length, you don't have any confinement for the beam reinforcement. So you have to consider confining some of the beam reinforcement. But if the column is small, like 400 by 400, then it may not be a major problem. So as the width of the beam, I have selected 450 millimeters. 450 millimeters. So the depth of the beam is considered as 900. Width of the base is considered as 450 at the web. But we have to also decide this particular width. And in the early example, we used 2.2 meters as that particular width. And if you want, you can use 2.2 meters for this example as well. But what you have to keep in mind is with the introduction of inverted T, the weight of the base is also reduced. So we have a lesser weight for the base. Because of that reason, we might be able to use a higher net bearing pressure. And when you look at the weight of this base, this will have a width of 2.2 meters, overall depth of 900 millimeters. And I'm going to use something like 300 millimeters for this particular flange, 300 millimeters for the flange. And so because of all this, we can say the weight of this inverted T could be equivalent to about 0.4 meter thick concrete, 0.4 meter thick concrete. So based on that, you can work out the new net bearing pressure, which will be about 190 kilonewtons per meter squared, which is based on the approximate calculations. So the net bearing pressure will be something like 190 kilonewtons per meter squared. And on the basis of that, you can select the width of the base as 2 meters. You can select the width of the base as 2 meters. So based on that, you can work out the maximum bearing pressure, and that is the load divided by the area represented by each column, and that gives 268 kilonewtons per meter squared. And if you consider the width of the base of 2 meters, it gives a line load of 536 kilonewtons per meter. And it gives a line load of 536 kilonewtons per meter. So when I know the load, rather than using the table that we have used earlier, I can determine the bending moment by using a program like SAP 2000. So I'll show you that, in sub 2000 you can very easily create and select a beam having about 5 spans of 3.5, and then we'll define a material. Already there's a concrete. Under define, you can define a material, and we can make a copy of this concrete and say concrete 30, and we can, if you want, you can change these to 27 e to the power 6. These are typical values of concrete, and then can also define an inverted T by defining a new property where we are going to use concrete, and we can go with this beam. B1 is 0.45 and B2 is 2 meters and B3 is 0.45 and D1 is 0.9 and D2 is, let's say, 0.6 and D3 0, D6 0.3, this is 0. So you can define the section and also assign the concrete, new concrete 30 to that, and we say inverted T 900, indicating that the depth of the inverted T is 900, and we can select all and assign the frame section to that, and then we can extrude it. And see the section like that, and then we can select all and then we can define a load pattern called live, and a new load pattern, and we can apply, look at its 2D, and or else we look at it 3D and assign a frame load distributed. I just said live, and that is going to represent the soil pressure from below, and the soil pressure from below is has been calculated as 536. So I can assign minus 536 because that's a load acting upwards, and So these loads are there. Then I can actually ask it to analyze results. And can ask it to display the bending moment diagram under live loading, and you'll end up with this type of diagram having the hogging in the span, sagging under the columns. So similarly, you can look at it and ask it to display the shear force diagram due to the live load. So you can get the shear force distribution and the bending moment distribution, and we can make use of this to determine the reinforcement and also various other parameters like shear in the inverted T-beam. So we'll take a break now, and then after the break I'll start at 4:20, and then we'll look at the design of the inverted T in greater detail.